In lecture number 7, so that was the feedback I showed you in lecture 8, someone actually wrote, I'm not critical, just curious, like, is this entire thing going to be just about Gaussian processes? Is this like the entire course just Gaussians? No. So today, we'll put Gaussians aside at least for a bit. They'll come back, but we'll put them aside for a while. So, what other distributions do you know other than Gaussians? Anyone who's thought during the last, 6 weeks, man, so many Gaussians. When is he going to do the other distributions? What distributions were you thinking of? Binomial distribution? I'm going to write something down, so you have more time to shout stuff at me. Student T, Did Bernardo tell you the story of student Gosset, Sealy Gosset? No? T. What else? Laplace distribution. Which else? A negative binomial. What? A negative binomial? Oh, okay. Okay. What else? Poisson. Yeah, I was hoping for that. That's an important one. Underappreciated distribution. The beta. What else? The uniform distribution. Bernoulli, great. Bernoulli is maybe the most elementary. I hope that's the right way to spell Bernoulli. Say again? Hyper-exponential. Hyper-exponential. Who's heard of the Helmert distribution? Oh, yeah, maybe you've heard of the chi-square distribution. So chi-square was arguably first discussed by Helmert. And I'm going to call it Helmert. It's a German physicist, not because I want to be, well, maybe it's a little bit, patriotic, but more because I just really hate this symbol. It's just nobody knows what that actually means. So, others? It's a good list already. I can add one more. Dirichlet. I'm going to call it the Euler distribution, which is the gamma distribution, but again, why just a symbol? It's a bit silly. Okay, and then of course we have the Gaussian, which I explicitly said we wouldn't want to have in here. So the lecture today, and also Thursday, and then maybe after the break even a little bit more, will be about actually all of these. But we'll do them all in one go. Actually, yeah, all of these, but there is one in here that's a bit odd out. And I'll leave it to you to think about this keep it in mind while we're going through the lecture, because it's a bit special. It sort of fits into the discussion, but not entirely. So why are we going to do that? So first of all, of course, right, in a lecture that's called Probabilistic Machine Learning, there should be more probability distributions than just Gaussians. Another way to think about this is more from a computational perspective. So I checked, Matthias Hein is doing optimization now, right? He's sort of moving from unconstrained to constrained optimization. And why is he doing that? Well, because he's doing statistical machine learning. And statistical machine learning is about estimation, right? You want to find one best guess for your latent quantity given data. And finding a best guess, the best thing, is an optimization problem. It's the computational task of estimation. We want to do probabilistic inference, which means we want to keep track of an entire space of possible answers, a volume of remaining probability, and where it is concentrated. And that's fundamentally a harder task. At least at first, it sounds like a harder task, right? Because keeping track of a volume is, well, it's just more to do, right? It's a more complex object than one point in a space. For example, in a discrete space, addressing one point has constant storage cost, right? I just need to store the address of that point. But storing a discrete probability distribution over that space is number of possible options along each dimensions to the power of the dimensions. So if you have binary random variables and you have n of them, you need to store 2 to the n possible values of these binary entries and then assign a probability distribution to all of them. That's exponentially hard in the dimensionality of the space. And so all of probability theory in practice, the stuff that we actually do on a computer, boils down to some degree to finding the right structures that allow us to do this task, tracking uncertainty, probabilistic inference, without expending exponential computational resources. And so I spent the first, basically half of the course focusing on the Gaussian, because in the Gaussian case, when the variables are linearly related, the entire task, all the tasks associated with probabilistic inference boil down to linear algebra. In particular, the sum rule and the product rule boils down to linear algebra, and therefore everything else, because everything else is just applications of the sum and the product rule. But as we noted at some points, Gaussians are just good for inferring the value of real numbers or sets of real numbers, vectors. And we saw that we can use these real numbers to also address functions in a function space, but it's always going to be a function space of real valued functions. And there are just some things in the real world that aren't real valued. Like sometimes things are discrete valued, or they have k possible options, or they are strictly positive. They might be a rate or a scale of something. They might be the bounds of some domain. They might be more rule-structured interaction terms, something like this. And then Gaussians just seem like really the wrong way to address stuff. And in a way, these distributions, if you think about them, they may have been invented by all these people. Notice that most of them are associated with someone's name. The beta distribution, by the way, could also be called the Laplace distribution, because it also comes from Laplace. And the Bernoulli is basically just a variant on the binomial, a different way of writing things. All invented to address certain base type of inference tasks, right? Inferring probabilities, binary probabilities, scales, categorical probabilities, rates for the Poisson, and so on. Now, it turns out that all of these, so they were chosen by their inventors, effectively, because they were searching for ways to do the inference on a piece of paper. I mean, these are also basically old white men, right? Because it's like 100-year-old stuff. So they had to do things with a pen on paper, actually probably with like an ink pen on paper. And so they came up with a particular structure that worked for them in every individual case. Now, it turns out that structure is actually always the same. And without knowing it, all of these guys did effectively the same computation in a roundabout way. And so I'm going to save us all time by not introducing all of them, one after the other, like in a classic statistics lecture, but doing it the computer science way by exposing you directly to the algebraic structure that makes everything tractable. And then we're just going to like marvel at this for 2 lectures, appreciate the structure. And that structure is now called an exponential family. It's not called the exponential family because there are many of them. Each of these, with one exception, forms an exponential family, maybe with 2 exceptions. And here's the definition of an exponential family. It's a particular structure for a family of distributions over a random variable x. So let's consider x. It takes some values that are somehow embeddable in a real vector space. But they can be a strict subset, like discrete values, for example. A probability distribution for x, which is parameterized by a parameter w, that has this form is called an exponential family. So what is that form? It's an exponential function. That's obviously where the name comes from. And then in there, we have a function of the a function of the random variable x, and I'm using the same symbol that we used in the Gaussian regression case, where we called this feature. Here they're not going to be called features anymore, but you can think of them as a little bit like features of our observations x, which are called the sufficient statistics, and we'll find out in a moment why. So think of this as we are observing x's. They are samples from some probability distribution, and we are now, there's this whole space of all possible probability distributions over x. We're not going to consider all of these, but we're going to constrain our search space somehow, our hypothesis space, to probability distributions over x that have this form, that are parameterized by w, and what we would like to know during learning is w. These w's, if they have this particular form, are called natural parameters of the distribution. So why are they natural? They're natural because they show up linearly in this term. So there's an inner product here between these sufficient statistics and just those numbers, no transformation. That's why they are the natural numbers. And then where there are two additional functions, one of them is only a function of x, and the other one is only a function of w. The one on x is easy. It just sort of defines a measure over the domain x. And in many cases, we can actually take it to be the uniform measure, and then it doesn't matter, so the Lebesgue measure. In some cases, this doesn't work if the vector space is too large, and it has to be some other base measure. But they're called either the base measure or sometimes nowadays also the carrier measure. Not so important. The important bit, though, and it'll turn out that this is really the business end of this entire thing, although initially it just looks like an afterthought, is this g of w, which we can think of as the logarithm of the normalization constant of this probability distribution. Why? Well, because we want this to be a probability distribution over x. So if we integrate over this expression, the one without the g, then we get something out that is supposed to be, well, we want the whole thing to be a probability distribution. So the integral over this entire thing has to be 1. Without this g of w, it wouldn't be 1. So we choose the g of w such that it is 1. And then this g is the logarithm of this z, where z is the normalization constant. And then this g is sometimes called the log normalization function or the log partition function. Partition comes from physics originally, where also some of these distributions come from. So, first of all, now I've just thrown this at you. Why is this interesting in any case, in any way? Let me highlight a few things. So what we're doing is here, we don't actually ever have a raw x in here. So one nice aspect of this is that we can deal with x's that can actually have a relatively general structure. We just have to be able to embed them somehow in numbers to be computable on a computer, like integers or real numbers, and then we can just compute functions of them. And then their interaction with the rest of the distribution is completely mediated by this function. Arguably also by this h of x, and this is maybe the second thing to point out, you may notice that this definition is not entirely unique. So I could, given such a representation of a probability distribution, I can move around a bit of the interpretation, and then it stays within this structure. For example, I could say there is an extra parameter w that I just set to 1 all the time. And then I could move h of x over here and think of it as some kind of bias term, if you like, right? And that's maybe fine, but it's just customary to move it separately and treat it as an extra thing, the carrier measure. Another thing I could do is I could basically put a 1 in between phi of x and w, and then split that into a map and its inverse, some invertible linear map, that's down here. And then you would get the same distribution, but different w's and different phi's. So up to such isomorphisms, this is a unique definition. Everything else just really doesn't matter, doesn't change the distribution itself. And then maybe just to, I know that at first when you see the structure for the first time, it looks really complicated. the main thing to focus your eyes on are the phi and the g. So phi, the sufficient statistics, and g, the log partition function. These two things define mainly the distribution, and they are the bits that we are going to be thinking about. And so I said that this is going to be a computer science-y introduction. So what I'm actually doing here is I'm writing down an algebraic structure that we're going to leverage for the entire next 2 lectures. And what is an algebraic structure from a computer science perspective? Well, it's an abstract base class, if you like. So here's a very complicated piece of code. What I'm saying is this definition I just showed you, being an exponential family distribution, means that you are a representation of such an abstract base class called an exponential family, ABC for abstract base class. What's an abstract base class? So it's a class that already has methods defined that aren't instantiated yet. And then it turns out that if you know that some of these methods are going to be instantiated by a constructor, then you can predefine methods on that class that become callable the moment you instantiate the class, right? So the definition from the previous slide basically says, to define an exponential family, you need to give me 3 things. The sufficient statistics, phi, the carrier measure or base measure, which is a map of x. The sufficient statistics are also a map of x. And a log partition function, g, which takes in the natural parameters, w, and then returns a number, actually, a real number for each instance of natural parameters. And if you have these 3 things, which you need to create, then we can create functionality. At first, we can only, so for now, we can only create the thing I've defined on the last slide, which is the probability density function of this exponential family, which is given by, well, this equation that was on the previous slide. And as an equation, is much more elegant and beautiful than as a piece of code. So we take in x, we make sure it's an array, we evaluate the sufficient statistics, we take an inner product with the natural parameters, we make sure that everything is broadcast in the right way. Then we add the carrier measure, we subtract the log partition function, and then that's the log probability density function. If you want to have the probability density function, you have to take the exponential of that. Okay, fine. I mean, defining probability density functions, yeah? So what will turn out, and I hope that you're gonna join me in appreciating this, is that this structure alone allows us to define many more methods to this class, which I'm actually not even going to show to you because they are going to be pretty obvious. And those methods will produce the kind of functionality that you typically want from Bayesian inference, from statistics, all the stuff that you maybe read about these distributions. Maybe you've been to Wikipedia, looked up one of these distributions because you had to for one of your homeworks, right? Like the Gaussian distribution, the chi-square, the binomial, the Poisson. And then if you go to Wikipedia, you get this little box on the right, right? That says, oh, this is this distribution. It has this probability density function, this mass function, this cumulative density function, this mode, this mean, this variance, this and so on and so on. It'll turn out that all of this can be automatically populated once you give me these 3 methods. Is that somehow cool? So let's see if that's actually true. So first of all, why are these, why do they have the names that they have, these quantities? The first thing is, why is it called sufficient statistic question?
Why do you need to supply the log partition function if that's just always chosen such that the integral?
The question is, why do I need to give you the log partition function if it's just the integral over this thing over there? And it's a beautiful question. The answer is exactly the other way around. If you give me the log partition function, you can get everything else, but integrals are hard. So if I give you a function phi and the base measure h, I have implicitly defined g, but you can't tell me what it is, right? Because integration is hard. There's a beautiful XKCD comic somewhere about integration being much harder than differentiation. Actually, it'll turn out that the entire game is going to be exactly the other way around. By giving you g, here's a little spoiler, advanced idea. If you give me g, if you give me one integral, if you tell me how to compute one integral in closed form efficiently on a computer, then that integral engenders all this other functionality, typically through automatic differentiation. That's going to be the entire game. So let's see why. First of all, why are these things called sufficient statistics? Well, let's say I collect not just one sample x, but many samples x from this distribution. I care about W. So I'm going to do some kind of inference that involves some prior on W, whatever it is. We'll talk about it in a moment. And then this as a likelihood term, where we have some data points x that are drawn IID from this distribution. So IID means there's a product. Then that means if you now plug in the definition for this exponential family from the previous slide, obviously, right, a product of exponentials is the exponential of the sum, and then we can just rearrange terms in the sum, put the brackets in the right place, and you see that the probability for all of these n individual samples is just the sum over their sufficient statistics, and then we take the inner product with the natural parameters, and then just n times the log normalization constant, plus a sum over their carrier measure. And obviously, these are quantities that I can store very efficiently. So if I have memory for one instance of phi and one instance of h, where h, again, is just one real number, so you could think of it as an extra thing to add to the list here, then I have enough storage to keep track of the entire data set. So every time a new x comes in, I just update this sum. Right? And updating a sum is constant cost, constant memory cost, constant compute cost. And therefore, after having seen these n instances, I still just have the memory cost of storing one instance. And that's why it's called a sufficient statistic. Right? So I need to, the phi's basically give me a representation of the x's that are the finite memory capacity that I need to store an arbitrary number of those samples. And now, in particular, then what I can do is Bayesian inference. I don't really tell you yet how to do it in practice yet. We'll need to think more about this normalization constant. But if I wanted to do Bayesian inference with a prior on W multiplied by this likelihood for capital X being the entire data set, actually the carrier measure will cancel out because it shows up in both the numerator and the denominator, and the posterior will involve just these sufficient statistics, so the sum over all the sufficient statistics of all the data in this data set, and that's it, basically, right? So the n just goes to the front, and we can work on this. Of course, so far, again, this isn't really fully Bayesian inference yet because there's an integral down here, and I haven't told you how to do this integral yet. We'll need to think about this. But now we know why this is called sufficient statistics, right? Good. So this could also be read as a negative thing, by the way, right? This means that such distributions, again, cast right, if you think of a space of x's and think of some really complicated distribution in this x space, then this representation means we're only talking about this distribution in terms of a finite number of features, whatever they may look like. So clearly, we cannot describe any arbitrary structure in our data set X this way because we're bound to a finite number of features of this distribution. Is that clear? A few people are nodding. OK. Then there's actually another structure which isn't all that important. It's a little bit like, you remember for Gaussians, I said the product of two Gaussian probability density functions is another probability density function of Gaussian form. There's a similar thing, actually it's the exact same thing, for exponential families, which is a generalization of that statement. The product of two probability density functions from the exponential family, from this one particular exponential family. So if I choose one set of sufficient statistics, one particular form G, that's one exponential family. If I have two members of that family identified by W1, W2, the product of those two, if I forever, whatever reason, have to compute that, this is not typically an instance of Bayesian inference, but some other reason might be there to multiply these. You can think of these as two different sources of information about X. Then, well, by plugging in the definition, we see that all we have to do is to add the natural parameters of these sufficient statistics. And then we'll get a new log normalization constant, which here looks like it might be complicated to compute because who knows what the difference between those two is. But actually, it's just going to be, you can maybe convince yourself, g of w1 plus w2, because integration is linear as an operation. So multiplying these probability density functions amounts to just adding their natural parameters. Okay, fine. Not that important. Now, the next step will be, I started with this argument. Let me just highlight that there are a few distributions that you've already encountered that actually have exactly this form, just to anchor your thought. But maybe already to help you a little bit to put this in the right corner of your mind, the impressive thing about this structure is actually not really going to be that it describes this entire space. I mean, that's one nice aspect of it. It's actually going to be even more general later on. We'll talk about other probability distributions that aren't in this list, which we can then create more or less arbitrarily in 2025 in a way that these people in, I don't know, 1905 or 1776 could not. But it's maybe a good part of the motivation to realize that these are instances of this structure. So actually, let me pick this one right up here. Here he is, Jacob Bernoulli, a Swiss mathematician that apparently spent his entire life in Basel. And careful, there are several Bernoullis. You have to be always make sure you get the right picture. This apparently is Jacob. They are brothers, I think. Here's the distribution. And maybe what this highlights, this slide is supposed to highlight also, is that sometimes this exponential family structure is not immediately obvious in the way that these distributions tend to be written on Wikipedia. And you have to mentally rearrange things a bit to discover that they actually are exponential families. So here is the distribution the way you've encountered it before. We're talking about the probability to observe k successes when performing n Bernoulli experiments. So I call this the binomial distribution. Actually, sorry. So the Bernoulli distribution is the case of just doing this once, right? And it's just q times 1 minus q. Or the probability is then just q to observe a success, right? If you do this n times and you talk about the probability of getting k successes, then it's called the binomial distribution. So I always get this wrong. So sorry, this is the binomial, which is the probability for multiple Bernoulli experiments. Let's assume we know how many experiments we do, n. Then, well, it has this form, right? It's the binomial coefficient for choosing k instances from n independently, sorry, not independently, but in an exchangeable fashion, and times the probability for the successes and the probability for the failures. So we can rearrange this because we want to have something exponential. So we introduce an exponential function, writing this with a logarithm. And then we can, having written it like this, we can identify the exponential family structure. So first of all, there is something out here in front. Realize that k now is our x. Right? In this instance, the number of successes is the random variable. It's x. So here is a function that only depends on k, assuming that we know what n is. And that's the carrier measure, h of k in this case. Then, inside of the exponential, there is a term that mixes parameters with a function of the random variable, and one term that only depends on the parameters. So this term is our log normalization constant. So minus n log 1 minus q is the log normalization constant, the log partition function. And here we see that k is actually the sufficient statistics. So in this case, the sufficient statistics are just the number of successes. And of course, right, if I observe 100 successes and then one more, it's easy to update that sufficient statistic. And it turns out that the natural parameters are this thing. They are called the logots, log of q minus log of 1 minus q. And so you see that sometimes the sufficient statistics are actually a nonlinear function of the parameters that we tend to use in the literature. Why is this? Well, because these parameters are maybe more natural to think about in a sort of the philosophical sense, right? So Q is the probability of a success, and 1 minus Q is the probability of a failure. But to get this algebraic structure, we need to write them like this. So now you can think about which of them is more fundamental. Yeah, okay. So we actually already encountered this distribution in lecture number 1, when I talked about the probability of people wearing glasses in a room, right? We encountered this binomial distribution, this product of Bernoulli success probabilities, and I went around the room. And back then, we did Bayesian inference on the parameter Q, right? The probability of success, which, as we now see, is a variant of the natural parameters of this exponential family. So what I did back then is, just to remind you, is to say, okay, so I need to do Bayesian inference. I need to multiply this with the prior. And then, I need to do Bayesian inference, so I need to be, I need to be able to compute this nasty integral down here. So I need to choose the prior P of W such that this integral becomes somehow tractable for me, and that I don't have to redo a new integral every single time I encounter more data. Now it turns out that, so back then I actually, I pointed out that there's a particular structure for the binomial distribution that we can use to simplify this computation. And that structure will now become a general property of exponential families. But back then, it was associated with a very specific distribution, the beta distribution, which is also here on our list, which is due to Pierre-Simon Laplace, who basically is the inventor of Bayesian inference. And this was also his very first use case of Bayesian inference, inferring probabilities. So I see something happening. The question, Aristotelian question, what's the probability for the sun to rise tomorrow, given that you've seen it rise every day of your life, and so on. Well, you have to infer a probability. How do you do this? Well, we're going to define, so realizing that this is our likelihood, so our binomial distribution for the number of successes n1, given that we've seen n0 plus n1 experiments, we want to know Q, we then chose to say, let's use a prior that has the same, I think I said back then, algebraic structure. So it's also a function of Q, where Q is raised to some parameter, and 1 minus Q is raised to some other parameter. In particular, if we choose alpha and beta to be 1, then this is the uniform distribution, which is here on our list. But we could choose other choices for alpha and beta, and then we'll get other distributions. So if alpha and beta are 1, it's a uniform distribution over the simplex. If I set alpha and beta to something less than 1, then I'll get distributions that look something like this. And if I set them to more than 1, I'll get distributions that look something like this, right? It kind of have a hump in the middle. And then you will know that if you set alpha and beta to large values, much larger than 1, you get something that's almost a Gaussian, and Laplace used this to build this approximation, and so on and so on. So here is this distribution, and it needs a normalization constant, which is the beta integral, one of the Eulerian integrals. It happens to be this integral, right, by definition, and it's actually related to this other Eulerian integral, the gamma function, by this equation, which Euler found out, really beautiful math. And then we found that under this structure, we get this really interesting behavior, that if we multiply this prior with this likelihood, then full Bayesian inference boils down to just adding alpha and n1 and beta and n0, and we always get back something of this algebraic form. So first, let's think about this in the concrete instance. Right? If I multiply a prior of this form by a likelihood of this form, you can see that clearly, right? You can just rearrange terms in the equation, and we'll just get something of the form q to n1 plus alpha 1 minus 1, plus alpha minus 1, times 1 minus q to the n0 plus beta minus 1. And then we need to normalize it, but we know how to normalize such distributions because we have this cool function beta the Eulerian integral number 2 of alpha and beta, and then we get a probability distribution that is always of this beta form. So first, let's observe that this beta distribution is itself an exponential family. So if you take this structure here, and you introduce an exponential again here, then you see that you can write this as the exponential of alpha minus 1 times log q plus beta minus 1 times log minus q minus logarithm of beta. And now we see that there is no carrier measure here. The carrier measure is the uniform, is the Lebesgue measure on the positive numbers. No, on the simplex here is the uniform measure. The uniform measure on this, because it's a distribution over Q. And the sufficient statistics now are log Q and log 1 minus Q. They are here and there. And the natural parameters are alpha minus 1 and beta minus 1. And the log partition function is exactly the logarithm of the beta function, of course, because we've constructed it this way. You following? Good. So, such a situation where we have found a prior such that prior times likelihood always gives back a posterior that is of the same algebraic form as the prior is called a conjugate pair of likelihood and prior, and the finding this prior is called finding a conjugate prior. So here's an abstract statement for this. A conjugate prior is something that's identified by a likelihood function, which is a distribution over some data set parameterized by some latent quantity x. And then we find a prior for it, which is a probability distribution over x, given some other parameters theta, such that the posterior is of the same functional form as the prior with updated parameters, where the update involves some update function, and it's not called phi accidentally. This is a computational statement, right? It's the ability to compute a posterior by adding some function of the data. So what this structure sort of gives us is, or what this describes is the ability to update a posterior by evaluating a function called phi and then just adding it to a bunch of numbers. This idea, by the way, of a conjugate prior is, well, it's actually maybe something that was invented over and over and over again, and arguably you could even say Laplace did it with the beta and the gamma, but there is the first paper I know of someone talking about this as an abstract statement is by Percy Diaconis and Don Ylvisacker from 1979. Who knows Percy Diaconis? So one of the downsides of me adding more text to the slides is that I can't put a picture here of Percy, but just Google Percy. He's like this larger-than-life persona, Stanford professor who doesn't have an email address, but has someone who reads his email for him. And he's 80 years old now, totally crazy life story. Left high school at the age of 14 to join a circus and become a traveling magician with like a card tricks, sleight of hand. Got back into high school at 24 because he got interested in math, studied at, I don't remember, MIT probably, or Harvard or something, and became one of the leading mathematicians of his generation. He's written about statistics and randomness and everything. He's been an advisor to casinos in Las Vegas. I once had the opportunity to invite him for a workshop in a casino, actually, in California. And actually not in California, but just about in at the state line to Nevada, and he talked about random number generators and how he could sit in front of a slot machine and figure out when it's going to give a jackpot and so on. A really crazy person. But he did a lot of contributions to basic statistics, and this is one of these like really cool ideas that come from him. Google has reserved the word Percy just for him because he's so important for this. Okay, so it'll turn out that every exponential family has a conjugate prior. And that conjugate prior is itself an exponential family. And that conjugate prior can be identified almost completely, automatically from the exponential family. So by writing down a set of sufficient statistics and log normalization constant, we are effectively identifying an entire machinery for Bayesian inference. I will do that derivation because it's the most complicated slide of the lecture after the break. What I'm going to do now is take the usual 5 minutes. See you then. I realize that this is, for some of you, this may seem like a lot of abstract nonsense. There were no questions in the break for the very first time ever. Maybe not a good sign. That means that might mean that I'm losing some of you, or that it's too slow. I don't know. So the Fachschaft Informatik recently approached me to tell me that they've done a poll, and people have said that in the bachelor course they want to have more theory. People are unhappy with the amount of theory courses being offered in the undergraduate class. And one of the lists so first of all, they gave me the responses with all the things people wanted. 80% of it was stuff that I was doing in my lectures anyway, and I was like, well, are people not paying attention? This is already in there everywhere. But there was a few things that we don't really do. One of them is category theory. It's one of these things that, first-year undergraduates always arrive at universities. Yeah, I do category theory. And maybe some of you have aged out of that. If you're the kind of person who always thought that you wanted to do category theory, maybe you should like this lecture today, because it's basically following the same kind of flavor, I think, of stuff, like just finding out where the structure is in all the computations that we're doing. For those of you who aren't that type of students, maybe let me draw a picture again. I realize I should have done this maybe before. One way to think about these distributions is, so the task we're going to solve is not to learn a function, but to learn a probability distribution. A probability distribution over some space X. Right? Let's say there's a two-dimensional space here. Here's a bunch of samples that you got from this space. This is, okay, in 2D it's a bit boring, but of course you can also think of the space of all natural images, the space of all cats and dogs, and images of cats and dogs, or three-dimensional representations of robotic policies that make you coffee, right? Then you would like to talk about this distribution somehow, and so you're going to cast it into some language of finitely many features. Let's maybe say we have a constant feature, and then we have a linear feature, and a bunch of features like this, right? So basis functions of this space somehow, and those are the sufficient statistics that we are computing. And then we compute a weighted sum of these to get some approximation of this probability distribution described in this kind of basis, right? Where the weights of these features are the natural parameters. And the log normalization constant tells us how to always turn this into a probability distribution. And this ability to make sure it's always a probability distribution is actually the hard bit, because you need to be able to integrate over a weighted sum of these features. Now, to do this inference, we need to take these samples, which will give us a likelihood. This likelihood is going to be an exponential family, right, by our assumptions. And then we need a prior over those weights. And now I just told you that there is always a prior that boils down this entire process into a sum, just adding up sufficient statistics, which is the cheapest operation we can do on a computer, right? And it's mediated by the sufficient statistics. We take our samples X, we transform them through phi, and then we're allowed to just sum stuff up if we have the log normalization constant. Here's the math for this. Imagine you have an exponential family. You've decided that your data set the x's come from such a distribution. Then there is a prior that is conjugate. And that prior is exactly this function. Every time I show this slide, people zone out. This is the moment to stay alert. This is the red meat, the main course of today's menu. That conjugate prior is itself an exponential family. So it's an exponential, there's no carrier measure, of an inner product between sufficient statistics and natural parameters minus log normalization constant, but now the roles are exchanged. So what used to be a natural parameter in our likelihood is now actually the object over which, the random variable over which we are defining a distribution. So they show up in the sufficient statistics. And the sufficient statistics are going to be actually, first of all, a copy of the natural parameters, and then the log normalization constant. So we need to know it. If we don't know it, we can't operate on this. And then there are natural parameters. We're just going to give them name, alpha and nu. So nu is going to be a real number, a scalar, because there's only one log normalization constant. But alpha is a vector, because the natural parameters w, there might be many of them. And it'll have a log normalization constant, which is implicitly defined by the integral over this thing. It's down here. So if you can do this integral, then you have your log normalization constant. And the problem is going to be, well, there's a new integral. We'll need to be able to do this. And typically, you can't. But sometimes you get lucky, and someone tells you what this integral is. If you do, then you can put your name onto this big list here. Why is this the conjugate prior? Well, if we multiply this distribution with this distribution, then we see that inside of the exponential, we can rearrange and we just get additive terms. Right? So the product of prior times likelihood as a function of w is exactly of this form, where the value alpha gets updated by phi x, so to alpha plus phi of x, and nu is upgraded by 1. So that gives an interpretation to alpha and nu. Nu is just a pseudo count. It's how many data points we have observed. It's just a counter, literally. It's the counter in a for loop, if you like. And alpha is a pseudo value, prior value of the sufficient statistics. So it's like you've observed a pseudo amount of new data points before you even start your experiment, and they had the sufficient statistics alpha. Another way to think about this sort of in a Pythonic language is these are the default parameters of your exponential family that you start them out with if you don't know anything else. Yes? Great question. So the question is, if I know G, so if someone has told me G, doesn't that mean that I know F? No, because F is this. And remember how G was defined, and we go back to the definition. So G is relative to this. So that's an integral over the sufficient statistics phi. Right? So we need to be able to do this integral. Let's ignore h for a moment. Let's say it's 1. Then we need to do e to the phi of x times w. That's one integral. Now we need to do a completely different integral. We need to do x of g of w dw. And that's just, in general, a completely different integral. You don't know how to do that in general. We will talk about how to do it approximately, but in principle, you can't. Now, so this is actually maybe the most important bit, right? So if I have this conjugate prior, then Bayesian inference is just summation. It's just call the sufficient statistics of your x, add them to what you have previously in memory, done. So if phi is a computable function, everything is now tractable, assuming that we have f. We can then actually also, so you can think of this as doing inference on the joint distribution P of x and w, because we can compute posteriors for w, and we can actually also compute predictives for x. So if you want to marginalize out the weights, if you want to compute an evidence in Bayes' theorem, if you like, or also if you want to predict future data, then you need to integrate out w. And we can actually do this, because if we plug in the definition of our original exponential family, so this one here, and then multiply by a prior of this form, then you see that the expression you get in the integral, so first of all, the carrier measure, of course, goes outside of the integral because it doesn't depend on w. And then what we're left with is an expression of the form that we now know how to compute a normalization for, that we now know how to compute because it is an instance of the log partition function of the conjugate prior, this new integral that we hope we're able to compute. So if we can do that, then this is just an instance of f minus the original f. So you can think of this, because they are log normalization constants, as a ratio of, so log ratio of normalization constants. So if you can evaluate f, you can predict future instances of x's. Question? So the question is, if you already have a log partition function G, why do we need a new log partition function F? So that's maybe the confusing thing. There are two different distributions here. One is the original exponential family, the likelihood. That is an exponential family, and it has a log partition function called G. And now I'm saying that exponential family has a conjugate prior, which happens to also be an exponential family, and it has a different log partition function F. And they are completely different functions. One of them involves an integral over phi of x times w, and the other one involves an integral over g of w dw. And this here is actually the complicated bit. This is not so complicated normally. Okay, so by the way, if you're following along, you may have been wondering which of these doesn't fit in here. Does anyone know which of them doesn't fit into the description so far? It's this one. The student t-distribution is not an exponential family, but it actually is an instance of this predictive form. So this here is the kind of thing you get if you have Gaussian distributions. Gaussians are exponential family distributions with unknown parameters. You do conjugate prior inference over their parameters, meaning covariance, and then you marginalize out using this mechanism, you get a student t. And you can see that this predictive is not generally an exponential family. So this is also a probability distribution over x, but it's not an exponential family in general. Right? If you don't know what f is, then this might be something very nonlinear of the parameters, well, alpha and nu in particular. Right? Okay, so what is this, like, maybe to also help you with your questions there in the back, it might be helpful to think about this from a code perspective, but I've learned that I shouldn't show you too much code, and I tend to get feedback that's a little bit too much code. So let me show you some code, which will be a very busy slide, but highlight the structure. So imagine you are an exponential family. You're an instance of that class. You're a probability distribution that is parameterized by some natural parameters, and you have sufficient statistics. I've already said that we have that, right? Then you know that you have a conjugate prior, because every exponential family has a conjugate prior. And this conjugate prior is identified completely by what you already know yourself about yourself, namely your sufficient statistics and your log partition function, and an extra thing, which is this new log partition function f. So you have g and phi, and if you would know f, then you would have your conjugate prior. So in code, this means that exponential families actually have a method called the conjugate log partition function f, which in general you don't know, so it's not implemented. Right? But if you know it, then you actually also have a separate method called conjugate prior, which you can call from inside of yourself. And you can say, please tell me what my conjugate prior is. I tell you what I am, who I am, what I tell you self, right? So I'm telling you my sufficient statistics, my log partition function G. Please figure out what my conjugate prior is. And then you can do this construction here, that this equation can be implemented in code, obviously. And once you have that, you can then do inference on yourself from a data set. So you have a method called posterior parameters, or you could think of this also as infer, or as posterior, or as learn is another way to call this method, right? Where I give you my prior, my alpha and nu, and then I give you a data set, data, and then you do posterior inference, which is this nasty piece of code down here, which effectively just means compute the sufficient statistics, add them to the prior, and count how many data points are in my data set, and add them to the pseudo count. To be able to do that, though, you need this log partition function. And then you can construct this other thing called a conjugate exponential family, which actually is an exponential family. Right? That's your parent class, if you like, your prior, your conjugate prior. And you can instantiate that conjugate prior as a constructor that takes in its likelihood. That's an exponential family. Stores it, and then it automatically self-constructs the sufficient statistics. It doesn't need any more input than that. It knows what its own sufficient statistics are. Why? Because they were on this slide. These are the sufficient statistics. It also knows its log base measure. It's the Lebesgue measure. It's just the log measure is just 0. And the only thing it doesn't know is its log partition function. So it'll have to call its likelihood and say, please tell me what my integral is. And then it might be that the likelihood says, I don't know. But if it does, then we're done. And then we have instantiated an exponential family, because remember on our definition on a few slides ago, these three functions completely determine an exponential family. If you don't have this log normalization constant, then what you can still do is evaluate your unnormalized log probability density function, the one without the log partition function. And we'll see why that might still be useful to have. Okay, that was the slow, the difficult, important bit. Have you been following along? So our goal is to do Bayesian inference. We found that we have almost everything we need if we know that our data comes from an exponential family, because we know what the structure of its conjugate prior is that maps inference to just addition using the sufficient statistics up to an unknown integral. And if we have that, then we can do Bayesian inference. But we can actually do various other things even so if we just have one exponential family without its conjugate prior. And they boil down to this table that you get on Wikipedia. So let me carry you through this one after another, pointing out a few properties. The first really cool and maybe most functional insight is that for exponential families, if you just have one exponential family distribution, computing expected values of the sufficient statistics amounts to differentiation. So if you want to know an expected value of the sufficient statistics, this might be something you might want to know for various reasons, then in principle, that's an integral, right? So what's an expected value? Well, it's this, right? It's an integral of our probability distribution against these sufficient statistics. And integrals are hard. In general, you don't know how to do an integral in closed form, right? But we can convince ourselves that we can actually compute this thing using basically integration by parts. It's just a mechanistic way of doing integration by parts. We're plugging in the definition of the exponential family. Then we realize that g of w doesn't depend on x, so we can take it outside of the integral. Because there's a minus here, it now shows up in the denominator. We know what g of w is. It's the log normalization constant, so we write it as an actual normalization constant. And then we can convince ourselves that this expression is the derivative of the log of this integral at the top. That's not so obvious at first sight. You need to stare at this expression for a little bit. But you know, what the derivative of the log is 1 over the expression times the inner derivative, right? Chain rule. So that's exactly what we have here. We get the phi of x down because that's the inner derivative with respect to w. So therefore, this integral, this expected value, is equal to a gradient of this function with respect to w. And that may seem like a minor insight, but it's actually extremely powerful because it maps an integral to a derivative. And derivatives are easy. You know that checks can do derivatives for you. You don't even need to think about them. They're just a call. It's a single line of Python code. And integration is very hard. So if we have a way of writing our probability distribution in exponential family form, then we have a way of computing expected values of phi. What might that be useful for? Well, let me give you the most important example. And here, for those of you following along, I'm going to make a connection again to Matthias Heinz's lecture, who's not currently talking about optimization. Why is he talking about optimization? Because he wants to do estimation, right? He wants to find maximum likelihood estimates of some parameters in a model, probably in a deep neural network or some other parameterized model. We'll get to deep neural networks soon enough. Okay, spoiler alert, these things will soon enough be deep neural networks, where we talk about the last layer of a deep neural network, and it's going to be an exponential family. But if you want to do inference in such a model, well, first of all, let's stick for a second with our course. What did I just tell you? If you have data that comes from an exponential family, samples of x, and you want to do inference, what is the thing you need to do? What you always need to do. Yeah, you need to do Bayesian inference, right? You need to apply Bayes' theorem, and for that you need a prior, and that prior is the conjugate prior. But maybe you don't know the conjugate prior because you need to know this nasty integral f that you don't know. So then you walk out here and say, this probabilistic stuff, it's all pointless. Let's go back to Matthias Hein. What has he told me? What did I need to do inference? I'm relieved to see that you're paying just as much attention in Matthias's lecture as in mine. You need to solve an optimization problem, right? You need to find the most likely estimate for W. You need to find the mode of this function P of x given W. How do you do that? Well, let's do maximum likelihood estimation. Let's assume you have a data set with samples from an exponential family. You would like to know what its parameters are. Then you can write down your log likelihood as a sum over these terms that show up in an exponential family. We just found out that that sum is particularly convenient to compute because it only involves a sum over the sufficient statistics. So that's called the sufficient statistics of the entire data set. Well, there's also a sum over the log carrier measure, but whatever, that doesn't depend on W, so it's going to drop out the moment we compute a gradient. Now we want to optimize this for W, so we take a gradient with respect to W. And that gives us this expression. I hope you will agree with me. And we set this to 0, and that means we need to solve this equation. So we need to take the sufficient statistics of our data set, which is an empirical estimate of their expected value. Right? It's the empirical mean of the sufficient statistics. Did I drop an n? No, actually, it cancels out because it's on both sides. Yeah, okay. And then we need to set it equal to the gradient of the log partition function. So in general, this is not a closed form expression. It's not something I can just solve, right? If I don't know anything about g, I cannot write down that this equation can be solved, right? But I can feed it into an optimizer. So here's a gradient, there's a number. I need to have that gradient minus that number be equal to 0, so it's a root finding problem. And you've got slides from Matthias Hein on how to do this, right? So I don't need to tell you about this. What did Matthias Hein, by the way, tell you about such optimization problems? What's the next thought you have to have? What do you need to be careful about? Can you always solve this optimization problem? Is it going to be easy? That's the key word. It depends on whether the problem is convex or not. So let's keep that in mind. We'll need to make sure, need to check whether this is convex or not. For the moment, you should say, okay, so interestingly, if you have exponential family distributions, then maximum likelihood estimation is a root finding problem. Let's check in a moment whether it's a good root finding problem or a dangerous one. Before we do that, though, let me make a connection back to Bayesian inference. Maximum likelihood estimation is really dangerous because there might be maximum likelihood estimates that are particularly pointless, and then you want to do what with your problem from a statistical perspective? You want to regularize, right, to make sure that you don't get nasty estimates. What is the probabilistic interpretation of regularization? A prior, yeah. So here, we're optimizing a log likelihood. If we regularize, so we add a term that depends on the parameters, that's like adding the logarithm of a prior, which is the same as multiplying prior by likelihood. Question?
Yeah, I have a question concerning this slide. So we have shown before that this gradient is the expected value of our statistics. But isn't that what we have shown in the slide before?
So, this is a good question. And maybe the order of these slides is a bit dangerous. So I showed on the previous slide that this gradient is actually equal to the expected value of the sufficient statistics under the full distribution. So now we're saying there is an actual data set out there which may come from whatever distribution, we're just going to impose the assumption that it does come from the exponential family. Then what this equation says is you're setting what you know to be the expected value under this distribution to what you're estimating that expected value to be. So they are not the same quantities on the left and the right-hand side of the equation, but they are matched to each other in sort of their interpretations make sense, right? That's also what this this line is supposed to say. So now let's go back to regularization, prior inference. So if I wanted to do full Bayesian inference, I would need the conjugate prior. We know that it exists, but it involves this integral that we don't know. But we can do something half-hearted. We can say, well, I know what the conjugate prior looks like. I just don't know its normalization constant. So let me do maximum a posteriori estimation. So find the mode of prior times likelihood, because finding that mode does not require this log normalization constant. And you know from this nasty piece of code that I showed you before that you can compute that unnormalized log probability density function automatically for any exponential family. You don't need to write any new code. The stuff, this fancy Python code on the previous slide, already does that for you. So let's pick the conjugate prior for our problem and add it to our, so add its logarithm, multiply it with our likelihood. Then we can do maximum a posteriori estimation rather than maximum likelihood estimation by adding to the log likelihood the log prior. Oh, that's not right. Oh, that's right, yes, log posterior. So the difference to the previous slide is that the order of w and x in this expression has been exchanged, right? Now it's log of p of w given x rather than p of x given w, which is an actual probability density function. And the differences are really minor. The only thing that's been added are these extra parameters alpha and nu, which now you can think of as a regularizer on our likelihood. We add them in, and then we find that we basically have to solve the same type of problem as before. We just have to set our actual expected value of this exponential family to a regularized estimate of the empirical mean of the sufficient statistics. That is weighted by how many data points we have in the sample and how many we think we had in the prior. So maximum likelihood estimation and maximum a posteriori estimation are basically the same thing. They just involve extra numbers if we have exponential families. So to summarize what I've told you on inference with exponential families so far, if I give you a data set, arbitrary draws from some probability distribution, assuming they are IID, then the mechanism for general inference on them is going to be I impose the assumption that this data comes from some exponential family. That means I'm going to parameterize the space of probability density functions over this domain X in some particular way that has this exponential family form. And that's a relatively general language. I just need to be able to write down sufficient statistics and their log partition function. And that log partition function is the hard bit. If I've done that, then I can do maximum likelihood estimation by solving a root finding problem. I can do maximum a posteriori estimation because I know what the conjugate prior is automatically, and the root finding problem just gets regularized as a result. And if I'm lucky and I even know the log normalization constant of the conjugate prior, this extra second integral, then I can even do full Bayesian inference on this unknown probability density function, yeah, or probability distribution more generally. And even better, that full Bayesian inference, when I say I can do it, that just means I can, what I need to do it, the actual computation on a Turing machine is evaluate this function f, the log normalization constant of the conjugate prior, at a point that is equal to the original parameters plus the sufficient statistics of the data set. So the only thing I need to be able to do is compute the sufficient statistics of the data set, add them to a floating point number or a set of floating point numbers, and then evaluate another hopefully computable function f. And then I'm done. And if I can't do this full Bayesian inference, then I fall back to one of these, maximum likelihood estimation or maximum a posteriori estimation. And now just a moment. The only question left to do is, have I actually told you something interesting here, or have I just told, oh, that is just optimization. Optimization is easy, and Matthias Hein has told you how to do it. No, because you still need to make sure that this optimization problem is actually somehow tractable. And you said exactly the right thing. One way to know that your optimization problem is in some sense easy and solvable is when it's concave or convex. Well, if the maximization problem is concave or the minimization problem is convex. So let me show you that exponential families are actually a log concave. They pose a log concave optimization problem. Or there are functions that are log concave in their parameters w. And so here's the sentence. All exponential families are log concave. That means the log PDF, this function, is a concave function of w, which means if we maximize it, that's like solving a convex minimization problem. So to do that, we write down the negative second derivative of this function with respect to w. If that's a positive definite thing, then we have a convex problem. So that's, you can convince yourself that by the form, so remember that an exponential family is just something that's linearly relating to, it's an exponential of an expression that's linear in the natural parameters with the sufficient statistics minus g of w. Because it's linear with the sufficient statistics, that term drops out in the second derivative, very convenient, because then we don't have to worry about the sufficient statistics anymore. And we find that we just need to compute the second derivative, the Hessian, of the curvature of this log partition function g. But we know that g is the expected value of the sufficient statistics. We just derived that a few slides ago. So what we need to do is effectively, so the gradient of g is the expected value of phi. So the Hessian is the gradient of the expected value. The second derivative is the derivative of the derivative. To do that, we plug back in the definition of what an expected value is. That's this thing. Then we apply the chain rule, a bunch of things in here. It's just standard differential calculus. I'm not going to do this like term by term. You can convince yourself afterwards. And you'll find that what you need to compute is the expected value of the outer product between the sufficient statistics minus the outer product between the expected values of the sufficient statistics, which is the definition, the statistical definition of a covariance. Right? And covariances are positive definite functions. We've talked a lot about covariance functions for Gaussian processes already. Here they are again. It's just a different covariance function. So the curvature of exponential families, of the logarithm of the probability density function, is positive definite. And therefore, finding the optimal w is a convex optimization problem, and therefore always tractable. Potentially numerically tractable. That doesn't mean you can do it on a piece of paper, but you can call an optimizer and you can forget about it. It's a fire and forget type problem. You call your BFGS, your nonlinear conjugate gradient, your constraint optimization problem solvers that Matthias Hein will tell you all about. And here's one of these beautiful moments where I can say, let Matthias Hein tell you about this, because he will do the entire theory of these optimization methods. And here's also the connection between probabilistic and statistical machine learning again. In the statistical sense, we want to make sure we can estimate by designing optimization problems that are numerically tractable. On the probabilistic side, we want to make sure that we can track uncertainty by defining structures that allow us to algebraically keep track of posterior covariances or posterior moments or some kind of other geometry of posteriors. And exponential families are the structure that gives us both. They give us a tractable posterior up to the normalization constant. And that tractable posterior forms a convex set of choices in which optimization is easy. But actually, there is one more thing, which is what Steve Jobs would have said. These exponential families actually have a lot of other extra cool functionality that is just baked in automatically by this structure. It turns out that there is an entire list of things that you can compute making use of the fact that expected values of sufficient statistics are equal to gradients of the log normalization constant. So without doing the derivations, let me just tell you that the Fisher information matrix, the entropy of an exponential family are tractable. They involve just computing second derivatives of the log normalization constant or derivatives of the log normalization constants plus the log normalization constant minus, well, expected values of the carrier measure, but you get to choose basically the carrier measure, so it's usually a very easy integral. The cross entropy between two instances, members of the same exponential family, is again something you can compute with automatic differentiation of the log partition function and the log and expected values of the carrier measure. Kullberg-Leibler divergences, so a way of measuring distances between, or divergence more precisely, between members of exponential families, are closed form expressions that involve gradients of the log partition function. The score of a exponential family distribution involves a gradient of the log partition function. The expected score, and so on and so on. So all these things that you can read up on Wikipedia about the Dirichlet, the Bernoulli, the hyperexponential, the chi-square distribution, the Dirichlet distribution, the gamma distribution, the uniform distribution, the Poisson distribution, they are all automatically constructed. They're just derivatives of some algebraic expression. And you could write a program that automatically writes the Wikipedia entry for our exponential family, right? We could add a method to this exponential family class that I've defined on previous slides that puts out the Wikipedia article, basically, adding all of this functionality. Or maybe a little bit like less humorously, all of these are methods of our class. So I don't show you the code for this, but you can implement a method called entropy, score, KL divergence, and so on, that takes in members of our exponential family and returns this. So I have like 9 more minutes, so I have slides that just point out the obvious, which is that other distributions on this list are also exponential families. And one particular fun one is the Dirichlet distribution, which I'll just do for fun in 3 minutes. But we don't even have to do it. If someone has urgent questions now, we can also discuss questions. Yes? Oh, your question is, if the conjugate prior is equal to the likelihood itself, is it then always Gaussian? I don't know. Actually, no, it's not. No. So there are instances where the conjugate prior is of the same form as the likelihood, but it's not a Gaussian. Look up the Poisson distribution. Good. Okay. Good. So here is the story of the young son of the guy from Dirichlet. So the story about this man is that he grew up in the northwestern corner of what is now Germany and sometimes Belgium, and there was a different time. And his father came from a village called Dirichlet or something. And so his father was Dirichlet, and he is le jeune Dirichlet. He's the young guy from the son from the guy from Dirichlet. Mathematician, lived contemporary of Carl Friedrich Gauss, who worked on various sort of these typical geometer problems that people were studying back then. And one of the questions that he encountered is this, basically the generalization of this beta binomial situation. If I observe instances from multiple classes, not just yes or no, not just varying classes, not varying classes, but instances of, I don't know, let's say, 5 different types of things, and I want to know the probability for each of these, then there's a generalization of these to discrete probabilities. So those are the, let's say, the categorical distribution, which isn't on this list, but it's the generalization of the Bernoulli. The categorical distribution is also an exponential family, which you can convince yourself of by looking at this representation. And I'm going to save us some time by not spelling it out. You can look at this later on. Then that's an instance of an exponential family where, so the sufficient statistics here are the counts, and the natural parameters are the log probabilities, the logarithms of the probabilities for each class. And the conjugate prior in this case actually has a known log partition function. So the conjugate prior in this case is the distribution that is named after this man, the Dirichlet distribution. It's constructed from our slides to be this distribution, a product over the probabilities raised to some parameter. You can see that this is a generalization of the beta prior for the binomial distribution. And its normalization constant is this thing, which is called the multinomial beta function sometimes, or multivariate beta function, which in a way is an intractable function, if you like, right? It's not something, well, it's just this, right, involving gamma functions. But we have nice little libraries because someone spent a lot of time implementing those to get a very good approximation to them on our computers. So we can call them, and then we can do tractable inference over categorical data using these Dirichlet priors. So if you've encountered problems where you need to estimate discrete probabilities for more than binary set of possible options, you may have already done Dirichlet inference effectively. And if you have time later on and towards the end of the course, I might talk about how this used to be the model for natural language processing a long time ago when I did my PhD, long before transformers and large language models, where you basically keep track of what do you need to do. Your natural parameters are the counts of how often you've seen each instance of the class. The log normalization constant is this thing, and it actually has a gradient that is also typically implemented in numerical, like in scipy.special or scipy stats. Why? Because you need it to do all this type of all these functionalities, entropies, cross entropies, Fisher information matrices, estimating most likely parameters, and it has a fancy symbol called the di-gamma function. As you already found out actually on a previous exercise sheet, of course, the Gaussian distribution is also an exponential family. I just feel like I have to say it out loud once, but you probably know. In fact, here's a long list of various exponential family distributions. Let's see which ones are on there and not on here on the slide. So there's the Bernoulli distribution, the binomial distribution, the Poisson distribution, the Laplace distribution, the chi-square distribution, the Dirichlet distribution, the gamma distribution. There's one that you didn't call out, the Wishart distribution, which is a generalization of the gamma to multivariate, so to covariance matrices, to positive definite matrices. The Gaussian distribution, of course, and the Boltzmann distribution, which is something that's quite important for physics, for thermodynamics. They are, so mentally, that's maybe the last thing I want to tell you, you can now store these in this sort of part of your mind that stores the quaint old ways in which people used to do computation before there were computers. So when science involved people writing on a piece of paper to do some fancy math, so people with names like this, they had to find one integral that allowed them to write down their one distribution. I'll do an example of this on Thursday, actually, to highlight this structure. And they did this for what they thought were important base cases, and in fact, they are important base cases. Just like a programming language has base types for important instances like strings, floats, integers, lists, and so on, these probability distributions provide some kind of base data types for elementary types of inference problems. If you want to infer the probability for a coin to land heads or tails with an unknown bias, you use a Bernoulli distribution, or actually maybe a binomial to estimate a parameter. It's an exponential family. If you want to know with what rate you're getting emails every week, you use a Poisson distribution, or how often the bus arrives, and so on. And if you're building a physics model for thermodynamical systems where particles are interacting pairwise with each other, you keep track of their interaction terms, and that's the Boltzmann statistic. So all of these, we now realize, are special cases of algebraic structure that we've now been studying in this abstract category-like way for all of today. They are all exponential families. And why is this useful? Well, because the people who did these derivations, they effectively always made use of this particular algebraic structure, which allows us to generate all of this functionality. It allows us, first of all, to do efficient statistical estimation of their parameters, either in a statistical sense by finding modes of the likelihood or a regularized likelihood that you can think of as a maximum a posteriori estimate in the form of a convex optimization problem, or given an extra ingredient, namely the log partition function of the conjugate prior, full Bayesian inference, resulting in a posterior measure over the parameters. And in addition to that, we get as like a little extra bonus all sorts of other information theoretic quantities, like Kullback-Leibler divergences, Fisher information matrices, scores, and so on, all as methods that can be automatically populated for this abstract base class. And for a long time, this list of things used to be taught in stats classes as a tool that people could use to do inference. These days, of course, you're coming here waiting to learn about deep learning and neural networks. So we'll need to make a connection between this formalism and deep neural networks. You can already think about this if you like. We'll do that after the Pentecost break, actually, and begin to think about it on Thursday, where I'm going to highlight, basically do an example again to highlight this structure. Please give feedback, but more importantly, fill out the internal departmental evaluation, and I will see you again on Thursday.